say a few examples of spectroscopy methods to quantify microplastics in marine samples. Then I will move to fluorescence methods. Finally, mass spectrometry methods. I will give one example. Okay, so as outlined, I will explain briefly where I'm coming from. I'm coming from a research center called CCMAR, a Centro de Ciências do Mar, Marine Sciences Center, based in the south of Portugal. Okay, so this center has over than 150 PhDs, including professors and researchers, and more or less the same number of students. Okay, so this is a map of our collaborations with our institutions. Oops. So as you see, mainly in Europe, but we can reach other places of the world, of course. We are members of the EMBRC. EMBRC means European Marine Biological Resource Center. So we are members. That is European infrastructure for research, for marine biology and marine sciences in general. So I have to, because of this problem of the contamination by plastic materials and microplastics, we decided to open a research topic in our laboratory that is analysis of microplastics, okay? So the goal is to set up an analytical workflow because there is no single method to analyze microplastics. We have to combine different methods to identify and quantify nano and microplastics in water, salt, sand, and marine organisms in order to support the development of plastic-free blue biotechnology processes and products. Okay, so we can, organize the available methods to analyze microplastics in 3 groups. One group is spectroscopy methods. That includes mainly IR microscopy and Raman microscopy. There's also mass spectrometry methods and fluorescence methods. I will start with that group over there, the spectrometry method, and with infrared microscopy. We have one of those instruments that can sample information from the particles we are analyzing in reflection mode, in transmission mode, in ATR mode. This is a typical spectrum of one particle. For those who are used with this instrument, this is a clean spectrum of a particle of polyethylene. This is one particle. And then another particle that is degraded polyethylene. We can see the OH and CO signals indicating that oxygen is being incorporated into the matrix of the particle, okay, after degradation. So basically, what is infrared microscopy is an equipment that combines an optical microscope that allows you to observe the particles and count the particles, quantitation, and together with an infrared spectrometer that allows you to take the IR spectrum, and then with comparison with libraries of spectra, you can identify the particles you are observing under the optical microscope. So summing up, that's how it works, okay? But there's a problem here. We are analyzing one particle. This was one particle of polyethylene and another particle of degraded polyethylene. This is one by one spectrum. And this for a sample that contains, say, 1,000 of particles is really, really difficult to perform. It can take 1 day or even more to analyze a single sample. And that is impossible. So we have another way to use our instrument that is under transmission with silicon filters. Basically, we use silicon filters. They are tiny filters, 1 centimeter square. They are transparent to IR radiation. Okay, so we filter using a system like this, common filtration. Filters look like that. And at the end, we can observe and map a filter with all the particles on it. Okay, and then we have an application of the software that is able to automatically get the spectrum of each particle on the filter, and at the end generates a report with the number of particles and their identity. But even this method is quite slow. It might take, say, 2 hours or even 3 hours to automatically analyze a single sample using this procedure. So the analysis of microplastics in natural samples is really time-consuming, is not that straightforward. Okay, so this is one example. We have also to say that this technique can go down to 10 micrometers size particles, because below that it is difficult to get a spectrum, or even physically impossible to get an IR spectrum of a particle below that size. Okay, so we have to move to other methods. Okay, one of the methods we have been exploring is fluorescence, but usually fluorescence for microplastics is not really a direct method for quantitation. People used to add to, you have a sample, you have many particles, you don't know what particles are microplastics, okay? So usually you had a polarity probe fluorescent, okay? And so if you had a probe that is hydrophobic in a natural sample, the compound will migrate into the selected hydrophobic particles, microplastics, okay, and make them shine. Okay, that's a way to, increase the selectivity of the analysis towards these microplastic particles. But we want to do more than that. We want to really quantify the particles using fluorescence. And to do that, we can, so fluorescence, we can use a fluorescence spectrometer like that one. That is a system that can be used to study fluorescence in solution, transmission mode, but also solids. So I can get a fluorescence spectrum from a solid sample, okay? In the so-called front face geometry. Basically, you excite your solid and then you get the emission spectrum, okay? You can do that for a solid, or can do that for a liquid. So why are solids? Because we want to analyze samples of sea salt and sand without any processing. Just take the sample, add your probe, and get the spectrum. As simple as possible, okay? So we explore this. To explore this, we choose polystyrene particles. Also, polystyrene particles covalently linked to NIRED. That is a polarity probe that is probably the most used for microplastics. And then we use these probes NIRED because it's known and used, and also start using pyrene. Okay? So what we know about NIRED is in these two papers from the 80s. So it is a well-known polarity probe known from the photochemistry community. So I'm originally a photochemist. That's the reason why I know this. So what we know about NIRED is these two things that is very important. First, the maximum emission is sensitive to the polarity of the solvent. There you have there 575 for benzene and 642 for methanol. There's a huge change of the emission maximum. And on the top of that, what you have is even an increase in the emission. Look at this, you have in ethanol 0.1 as compared to 1 in heptane. This is amazing. This is 3 orders of magnitude higher. Okay, so that's the reason why this probe is so good. So, but this is in solution. We want to see how it behaves in particles. Okay, so what we did first was to get the spectrum on silica. Silica powder looks like polarity, it should be similar to water. So what we got is that emission with a maximum of 644. And on salt, look at this. Very low emission, and the salt surface is quenching the emission. If we have two salt particles of polystyrene covalently linked to NIRAD, you have the emission of NIRAD, but the emission in the environment, as expected, in a non-polar environment supplied by polystyrene. Okay, so this is different from the top. Okay, and if you have NIRAD and then polystyrene non-salt, you basically have the same thing. So this means that free NIRAD is migrating into the polystyrene particles. And you have this shift with the maximum at 575. So this basically is similar to what happens in the solvent. However, this simple behavior of shifting the maximum is difficult to use for quantitation, directly to use for quantitation. It's very good. It stains the particles, so you can use that under fluorescence microscope, and you can see where the particles of polystyrene are because they are shining green. But for quantitation, for direct quantitation, it's not simple to use. So we move to another probe that is pyrene. This is the emission spectrum of pyrene with these two typical emission peaks of the spectrum, okay? And again, from the literature from the 80s, that's another known polarity probe. We know that the ratio between I1 and I3 is sensitive to polarity. Okay, so we try to use these differences to make some quantitation of microplastic particles. So this is, again, the spectrum of pyrene, and then we have the two bands. In the presence of polystyrene particles, you see that this one increases, but these spectra are normalized at this emission peak, okay? And in polyethylene, look at that. So this works for particles, and we decide to use the intensity of this peak for quantitation purposes. Okay, so here we have an emission spectrum of pyrene alone on the surface of salt. If we have polystyrene particles, we see an increase in the emission. So basically we can use pyrene for quantitation, okay? Using the I3 intensity band, for example. Note that the emission is quenched, the entire emission of pyrene is quenched by the salt surface. So we can make some calibration curves, and you see there's a straight line there. So the response is linear between 0 and 20 micrograms per gram. If we expand that area near between 0 and 1, we see that it is also linear in that range. Okay, so for a real sample, okay, so this was published for a real sample in using the standard addition method. Okay, standard addition method is you pick up your sample and you spike it with different concentrations of your the compound you want to measure, and then make a straight line. And then the intersect here gives you the concentration in your sample. So that was obtained using a standard addition method. And then, as you can see here, the concentration in this case of polystyrene is about 2 micrograms per gram, which is 2 ppm, basically. Okay, but fluorescence gives an indication of the amount, but it doesn't tell you what particles you have there, if you have polystyrene or polyethylene, whatever. So you need an additional method to to see and check the nature of your particles. Okay, and the method can be mass spectrometry. Well, in mass spectrometry, you can use GCMS or LCMS. You have to transform your particles in molecules because you cannot analyze a particle using chromatography. You analyze molecules. Okay? So you have to make a reaction. And you have to identify the compounds that came out from your particles. So I will show now an example using GCMS. We construct this device here as a container for your sample. There's a closed glass vessel that collects the released compounds after heating in the gas phase. And there's a SPME fiber that collects the released compounds. And then it can be introduced into the GCMS and gives something like this. That is a GCMS profile. Each peak is a different compound. This was obtained by heating thermal degrading standard of polystyrene. Okay. And what are those peaks? Okay. GCMS, we have the spectra and the structures here. You know, styrene, benzaldehyde, acetophenone, and indenone. So these compounds are released after thermal degradation of polystyrene, pure polystyrene. But we want to analyze solid samples. Okay, so what we can do is to put sand in here and heat the system. And what we get is this complex many peaks profile. Okay. However, if we want to know if, for example, acetophenone is there, 120 is the molecular ion, you can make an extraction of this full scan profile and you get a peak there. And you can detect the presence of polystyrene using this compound or using any other of the form compounds. Okay? So this method is complementary with fluorescence. Okay? So now the team is this group of 5 persons. Here there's the 2 students, that's Inês and Camila, that worked in this specific project. We have also collaboration with a company that is producing salt and microbiology, that is Necton. And here some other collaborators, George from CCMAR, Luis Filipe from the Technical University of Lisbon, and Stefan and Ramamurthy from the US. Okay, and finally, our sponsors, and thank you for your attention.
Thank you. Open discussion is open. Questions about this topic?
Know if you were looking at other probes than these 2. You were looking only for hydrophobic probes, right? That will interact with polymers, which are hydrophobic. Think of other probes, other hydrophobicity.
Yes, there